Yeah, I'm very happy to be here. So thank you for the invitation. Uh, so it was a command, and the instructions were, and I love that. To give some kind of survey talk on exponential motives. Yeah, and I'm very obedient, so this is what I'm going to do. So this is a joint work with Peter Jossen. Which has been going on for a long time now. And the first thing I wanted to tell you is how it started, because it has a very concrete beginning, and it was a strong motivation for me. So let me start with this. And the beginning was the gamma function. Okay, so the gamma function is defined by an integral. And you see that in the integral there is an exponential. And I was very interested in the values of the gamma function. Okay, gamma of n is n minus 1 factorial. So we can consider that this is not very interesting. But then if you take s a rational number, which is not an integer, then the values of gamma start becoming very mysterious. There's one example that we understand well, which is gamma of 1/2. So this is can also be written as the integral from minus infinity to infinity of exponential minus x squared dx. And this is equal to square root of pi. But then if you start considering gamma of 1/3, gamma of 5, and so on, these are kind of mysterious numbers. And one reason is that we don't expect them to be periods. Okay, so a period is something that you can write as an integral, but you need the integrand to be algebraic. Okay, and here you have an exponential. So then usually something is a period if, well, you can write it as a period, and if you can't, the kind of philosophy is that, okay, we know these numbers for a very long time. No period integral representation has been found, so it probably means that it does not exist, which is not very satisfying. And in this particular case, it's even more mysterious because if you do products of these gamma values, you find periods. So one example I knew very well is the following. So you take E to be an elliptic curve defined over Q bar. And then you consider the periods. So it means you integrate algebraic differential form. And actually, we are going to take a holomorphic differential. So it means it's a generator of H0 omega 1. Okay, so this is the form defined over Q bar. And then you look at the complex points of the elliptic curve. So this is a torus. And then you can take a cycle which has a non-trivial homology class. Let's call it sigma. And you can integrate omega along sigma. Okay. So this is a period of the elliptic curve. And the philosophy here is that if you take a random elliptic curve, then these are really new numbers. Okay, these are new numbers that you cannot write in terms of things like I don't know, pi or logarithms of the things we already know. And in addition, so in the elliptic curve, you have two classes that give a basis of homology. And if you take two linearly independent elements, these numbers have nothing to do with each other. There is no algebraic relation between them. Okay, so we don't know how to prove that, but this is what we believe. But there is a case, there's a special case where it's the case where E has a complex multiplication. Okay, so this means that the endomorphisms of E is bigger than just multiplication by an integer, so you can do multiplication by complex numbers. And if you tensor this by Q, you actually find a imaginary quadratic field. So I'm going to write this Q square root of minus D. And here I want a fundamental discriminant. So if your thing is Q of the square root of minus 1, you write square root of minus 4, for example. Okay. And then there's something called the Scholar-Server formula. Which tells you that in this situation, well, first of all, up to an algebraic multiple, this does not depend on the choice of the cycle. And you can write it explicitly as a product of values of the gamma function. Okay, you can actually write this as a product of gamma of A over D. So D is the same as here. And it goes from 1 to D minus 1. And then they appear with some power, which is actually a rational number. So this means that we don't expect each of these numbers to be individually a period, but if you start doing products with and clever combinations, they become periods. And well, this is kind of a bit sophisticated, but you can do something less sophisticated, which is you take this number and you put it to the power D, and then you can write this as a product of values of the beta function. So this is given by this integral. And now you see if S and T are rational numbers, then you can do change of variables using a common denominator. And this is an algebraic function. This will become a rational differential form of some cover of projective lines. So this is actually a period, and it's a period of a Fermat's curve. Okay, so this is not expected to be a period. If you take power D, is a period. So my thesis was about generalizations of this formula to more general situations where you have a algebraic variety with some automorphisms, and you can use these automorphisms to cut the cohomology into smaller pieces, and then you expect that the periods are also related to gamma values. And I was very, very intrigued by all these phenomena, and in particular by the following, which is that there's a conjecture about the Arsenes properties of these values. So the conjecture is, it's a conjecture by Lange and Lear. And it says that if you take D at least 3, then you consider the numbers gamma 1 over D, gamma 2 over D, gamma D minus 1 over D. Okay, and then you want to know what is the transcendent degree of the field generated by these numbers. And you do the following. So we know that the gamma function satisfies a number of functional equations. So, for example, gamma of s plus 1 is s gamma of s. So this tells you that it's enough to stop here. But there's also a relation between gamma of s and gamma of 1 minus s. And there's also a product formula. Okay? If you use this relation, this tells you that the transcendence degree can be at most 1 plus the value of Euler's p function d divided by 2. Okay, so this is an upper bound for elementary reasons. And the conjecture is that this is an equality. Okay? So, it is a very hard conjecture. In particular, it says that this number is transcendental, for example. We don't know this at all if d is 5, for example. And because these numbers are not periods, not expected to be periods, this doesn't fit into Grothendieck's period conjecture. Or at least not in any elementary way. So what is Grothendieck's period conjecture? So the statement that if M is a motive over Q bar, okay, then this will have the RAM realization. So you can imagine M is homology of some algebraic variety defined over Q bar. So it will have the RAM realization, Betty realization. You can compare them. This produces periods. And then the conjecture said that the transcendence degree of the field generated by these periods is equal to some Galois group that you can attach to the motif. So in an ideal world, the category of motifs should be a Tanakian category. So you can consider this as a representation of some group. And the conjecture says that this is the dimension of this group. And to write GM, this is the motivic Galois group. And then this is a very beautiful conjecture that is very useful to make predictions, because if you are given a specific variety, then it might not be super simple, but you can compute this. Okay, and this tells you what you should expect for algebraic relations between these numbers. So I was familiar for different reasons with these two conjectures. And my initial motivation is that I want to see this one as a particular case of this one. Okay, and this is not expected to be possible in the usual framework because these are not periods. And then this is where exponential periods and exponential motifs are going to appear. Okay, so that was the motivation. Any questions about this? Okay, so I had some extra piece of information at the time. That was that, okay, this is not a period in the usual sense of comparing the Raman singular homology, but it's actually a period of a connection, a vector van der Waals connection. So this is something that I had learned in a paper of blog Eno. So if you open the old books about special functions, you will find that so you have a formula like exponential of 2 pi I s minus 1 times the gamma function. This is equal to an integral of this shape, exponential of minus x to the s dx over x. And you integrate, so here there's 0. So you integrate on a path that comes from infinity to 0. Then you do a circle around 0. And you go back to infinity this way. Okay, so you need a determination of x to the s along this path. And in this formalism of vector bundles with connection and comparing the RAM homology with kind of singular homology, so you have this cycle C. You have this function. And you integrate or you do a pairing between this and dx over x. Okay, so the idea here is that we are working on Gm. It's A1 minus the origin. This is an algebraic differential form on Gm. And we are considering the trivial vector bundle called the Gm. And this is a section, this is a flat section for a connection, so you need to write down the connection. And it's the connection that says 1 to minus dx plus s dx over s. Okay, so kind of knew that the gamma function had something to do with periods, but in a more general setting. So usual theory of periods is you take the trivial sheet, but then you put the trivial connection also. And in particular, this connection has an irregular singularity. So. Okay, so I was younger at the time, so I first tried to do the most general possible thing. Okay, so let's take all vector bundles with connection and do a general theory of motifs for those. And this works very badly. This didn't work at all. There are many different problems. One problem is that in general, you want to have associative local system, and this will, in general, only be a local system of complex vector spaces. And if you want to define periods, you need two rational structures, because to write down a period, you need to choose basis, and if you are able to change your basis by a complex number, then all complex numbers are periods. Okay, so this was a problem to do that. So I said, okay, let's be less ambitious. So let's just consider the case S is rational. Okay, and then if d times S is an integer, then you can actually write the gamma value essentially is the integral from 0 to infinity of exponential minus x to the d, so this denominator, and then x a minus 1 dx. So this will be a multiple of gamma of a over d. Okay, and then this is a simpler situation. So this is an algebraic differential form, and this is the exponential of a function. So it's also in this setting, but still the underlying vector boundary is going to be trivial, but the connection has a simpler form. And for example, there is always a rational structure. Okay, so I thought, okay, let's try to do this. And that was exactly the time when I started a postdoc at ETH. And Peter Jossen also arrived at ETH the same day as me. And we started talking about this and well. Okay. So that was the motivation. Questions? Yes.
So the series will be like once before if the connection take over OGM is trivial. So the section is just like a regular like function over GM.
Mm-hmm.
But if you take in your example, this section will in like a meromorphic function over GM, or there are more analytical items that we.
Yeah. So this is. Yeah, so this is a central question in everything we are going to do. So thank you. Okay, so you consider the OGM, there's the connection, and then you try to solve the differential equation. And if you have a global solution which is holomorphic, then it means the local system is trivial. Okay, and this is going to come soon. So this is a situation where you don't have holomorphic solutions, and the local system is non-trivial. Okay, this is not very hard to imagine. So if you do x to the 1/2, there will be monodromy around 0. Okay. So what you do is you just want a section which is univalued on some path. So it's not on the whole space; it's on some path. And then you can fabricate a homology where the elements are a path and a section which is holomorphic, but only on that path. Yeah. And there is no global. Other questions? Okay. Yeah, so now we are going to look at this integral. So exponential of minus f omega along sigma. And we want a cohomology theory for them. And it will be upgraded to a theory of motors. Okay? So, okay, so the situation is the following. K will be a subfield of the complex numbers. Maybe we'll talk about this later. This theory is very interesting for K, a finite field, for example, but it's a different story. So today is going to be a subfield of the complex numbers. And then X is some smooth variety over K. And you can imagine that it's affine, for example, it's enough to study periods. And F is a function on X, and I think of a function as a map to A1. Okay, so this is the data, this is K, the field, the variety, and the function. And then we want to consider integrals of this kind. So well, I need to tell you what is omega and what is sigma. All right, so let's start with omega. And if we do the RAM homology and periods, okay, the first thing we want is that the value of the integral does not depend on the choice of a representative of the homology class. Okay, this is the minimum we want. And this follows from Stokes' theorem. So we need to understand what's Stokes' theorem for this kind of integrals. And if you compute the derivative of this, you do the little computation and you find that this is exponential of minus f times d omega minus df Wells constant. Okay. And this suggests that if you want the ramp homology for these integrals, well, you should impose that this vanishes. Okay, so this is the thing that should vanish. Okay. And then once you've done this observation, there's no choice. So you define the ramp homology of x comma f as okay, so it will be the cohomology of a complex of sheaves in the size topology. I'm very old school, so I like to put a double bar and talk about hypercohomology, and it's like from another century. So you take the RAM complex. This is the complex of scalar differentials, the complex of coherent sheaves. Usually, you will send omega to d omega, but here you do minus df wedge form. You can see that this is a complex because this is just the conjugation of the usual differential by exponential of f. And so you can take cohomology. And this is called twisted the ramp cohomology. And well, observation is that if f is 0 or if f is constant, more generally, you are just doing d, and then you just find the usual algebraic ramp cohomology of x. So one thing that we want is that exponential motifs contain the theory of classical motifs when there is no function. Okay, so let's do a little example. Let's take x to be the alpha 9, say over q. So then yeah, regular function is a global section of the structure sheaf, so it's just a polynomial with rational coefficients. I'm going to take this polynomial to be x to the n. Okay. So then we can work with global sections because x is affine. So the ramp complex has two terms, qe x and qx dx. Okay, and what do? You take a polynomial p and you do derivative. Then you need to take the derivative of x to the n. So this is minus x and x to the n minus 1 multiplied by p and dx. Okay. And then there can be cohomology including this. H0 is the kernel and H1 is the co-kernel. First thing you see is that H0 is 0. Because, okay, what we are trying to do is to introduce the exponential of this function. And the exponential of this function is not a polynomial, so if you try to do this equal to 0, then you find nothing. So the interesting thing here is H1 the ramp. And here you see that, okay, the worst thing that can happen is that P is equal to 1, okay? If P is equal to 1, this is 0, and this is x to the n minus 1. So actually this thing has always degree at least n minus 1. So if you have dx, x dx, x squared dx, is not in the image, okay? And moreover, they are linearly independent. So dx, x dx, and x to the n minus 2 dx, they are linearly independent classes here. And then you do a little exercise to show that it is a basis. Okay? So this space is generated by these things. You can assume that n is at least 2 if you want that there's something. And yeah, this is a basis. Questions? Okay, so what is interesting already in this example is that here we are working algebraically in the Zariski topology, but then you can work analytically. Okay, meaning you do analytic topology, so instead of regular functions, you take holomorphic functions. So then this complex becomes entire functions on C, and then entire functions on C times dx. The map is the same. A function g will be mapped to derivative minus m x to the n minus 1 g dx. But now you try to compute, and you see that there's something in the kernel of this map, which is the exponential. So H0 is, let me write the RAM analytic. So this is one-dimensional, is C, because it's generated by the exponential of minus x to the n. And you compute H1 the RAM. This is the co-kernel of this map. But actually, this map is surjective. So you take any holomorphic function on C, and you can write it in this form by solving a differential equation. Okay, so this is safe. So you see, we get very different answers. In particular, algebraic, the RAM cohomology, and analytic cohomology are not at all isomorphic. And this is that algebraic and analytic the RAM cohomology are isomorphic is a characteristic property of connection with regular singularities. Okay, so this is a manifestation that the vector bundle OX with the connection, say that sense 1 to minus df has irregular singularities at infinity. Okay. So coming back to your question, since there is this global solution, which is the exponential, the kernel of the analytification of this connection is actually trivial. There is a global section. So this is C, the trivial local system. Okay. And what is always true for any connection is that if you work analytically, the analytic cohomology is the same as the cohomology of the local system. So it's a Poincare lemma. So there's a Poincare lemma. Telling you that the analytic RAM cohomology will be isomorphic to singular cohomology or the shift cohomology of the complex points with coefficients in the local system of analytic solutions. But then this is trivial, so this is just the usual cohomology of C. These are singular homology. Okay, and you see that we are going to have a problem if we look for cycles in the usual sense, because here I did the example of X, the affine line. We have a lot of homology classes, but the affine line is contractible. There's no cycles. Okay, so no interesting homology cycles. Example of the in this base of this. Okay. So, what is a homology cycle? So it's a compact cycle. It's defined as the image of a simplex. The simplex is compact. The application the map is continuous. So if we want to, let's go back to the integral. So we already know what is omega. Omega will be a class in this twisted around homology. And now we need the sigmas. And what this shows is that we cannot take compact sigmas. Compact sigmas will not be enough. Okay, so it means we need some sigmas that go to infinity, but then the integral may not converge. Okay, so if the sigma is unbounded, converges issues. Okay, but well, the situation is not so bad because omega here is algebraic, and this is an exponential. So what we need to ensure is that if sigma has a boundary, the exponential of minus f decays faster than omega on this boundary. Okay? And then the integral will converge. So this is a property which is very well known in analysis. It's called rapid decay. So what we need is actually that the real part of f, so the growth of this is controlled by the real parts. What we need is that the real part of f is very negative or very positive because there's a minus sign on the boundary of sigma. So we need to study what is the real part of f restricted to the boundary of sigma, if there is a boundary. Okay, so hopefully this motivates a little bit the definition I'm going to write now. So this is called rapid decay homology. Now it's typed down because it's homology, rapid decay. Okay, and there are two. Okay, the first idea is that we need unbounded cycles. Okay, so for example, let's go back to this. Okay, so this is on the affine line. F is x squared. And actually, the first time you learned about this integral, what you learned is that this is the limit as t goes to infinity of the integral between minus t and t of the same thing. And now, okay, so in other words, we are writing the real line as limit of intervals minus pt. Okay. So now this is compact. good, but it has a boundary. The boundary is given by these points. So what we are going to do is we're going to look at the region where the function f is very positive. So here it will be something like this. Okay, so like x squared is very positive here. And then we want limits of cycles that go to infinity, but only in the directions where f is very positive. So if you try to formalize this a little bit, you come up with the following. So you are going to define this homology as limit as t goes to infinity of relative homology, so take complex points of C. Then you look at the region where the real part of f is bigger than or equal to t, and you take a singular homology with rational coefficients. Okay. So what is an element here? So an element here will be a collection of sigma t's, which are, so here the transition maps are induced by the usual inclusions. And we want that the boundary of sigma t, if there is any boundary, is contained here. Okay, so the real part of f restricted to this boundary should be at least t. So this is the definition of rapid decay homology. Questions?
Maybe just a naive comment, like it seems surprising you can make an algebraic thing out of this. Like it seems such an analytic point of view.
This part is kind of analytic for sure. The place where it is, the algebraic part comes from the fact that X is an algebraic variety. So here you have a map from an algebraic variety to A1. And this has the property, for example, that you can stratify this map. Okay, so there will be a Zariski open inside, for example, such that when you restrict to U, this is locally trivial. There's a locally trivial vibration. So it means that, for example, this limit is not really a serious limit. As T is large enough, the maps are isomorphisms. And so this is something that will not happen for a general map. First source. And the second one is that actually you can represent things here by semi-algebraic maps. So it looks very analytic, and it is, but the fact that X is algebraic introduces some algebraicity. Okay. So that's the situation. So now we have two homology theories. Well, this is homology, but then you can define homology as the dual. Linear dual. And well, if you have two, like if you want to do a theory of motives, the like kind of minimal starting point is that you have at least two homology theories and you can compare them. Okay, so this is the following theorem. So it has a kind of long history in this final form is due to In and Walker. And it says that there's a unique punctorial isomorphism. Okay, that goes from the rank homology. So the rank homology is a vector space over K. You can tensor by C to make it into a complex vector space. And then it goes from here to rapid decay homology, which is a vector space over Q, you tensor by C. Okay, there's a unique isomorphism that for affine varieties is induced by the integration rate. Okay, so what does this mean? Okay, so it means that you have the ramp homology. And the advantage of working with affine X is that as before, you can compute using the global ramp complex. So actually every element here will be the class of a differential form. If you work in general, so this is hypercohomology, so an element is a bit more complicated. Here is just the class of a differential. And then you have rapid decay homology. So here you have some system class of sigma, or sigma is some system like this. And you want to produce a complex number. So how do you do it? Well, you map omega sigma to limit at t goes to infinity of integral along sigma t of exponential minus f omega. Okay. And we have set up the theory exactly for this integral to converge. F has rapid decay along the boundary. This is a well-defined complex number. Okay, so I should explain what functorial means. And to do this, first a remark. So this homology is already a relative homology because we are doing relative to this closed substance. But sometimes you wanted to integrate on cycles that have a boundary that has nothing to do with the function. We'll see an example in a moment. So it's very useful to extend these homologies and this isomorphism a little bit. So we can extend this to include a subvariety y inside X. So it means that there is actually a notion of the ramp homology of X, Y, F, and a rapid decay homology of X, Y, F. So this one is very easy to define. You just add the subvariety here. Okay, so you just do homology relative to this and the complex points of the subvariety. This is a bit more subtle, especially if y is singular. And in the application, you need at least that y is a simple non-Arthur universal. Okay. Doesn't matter. So this exists. There is this generalization and the comparison isomorphism also generalizes. And then functorial means well, that you have two varieties and you have morphism between them, and each variety comes with a map to A1. And this commutes. Okay, so another way to say the same thing. This is a morphism of X schemes over A1. And okay, let me write this without the similarity. So then you can do a pullback in cohomology. And this will send a cohomology class of X prime F prime to a cohomology class of XF. Yeah, then this is if I don't write anything, this is an operation that is true both on the RAM and on rapid decay cohomology. And it means that very soon it will be a morphism of motifs. Okay, so you have these maps. So you can imagine you create a diagram with these maps, and functorial means that this diagram commutes. And very concretely, this means that this is change of variables in the integrals. Okay, so this is the first property. Second property is that if you have y inside the x, close a variety, then you have a boundary map that goes from cohomology in degree n-1 of y to yf, f restricted to y, to cohomology in degree n of x, y, f. And again, the comparison isomorphism will commute with these maps. This corresponds to a Stokes formula on the integrals. Okay. And there's a third property, so the comparison isomorphism is also compatible with the Q-net formula. Okay, so the Q-net formula says that you can compute the cohomology of XF tensor, the cohomology of X prime F prime. And okay, so what is the usual Q-net formula is that this is, if you have no function, this is the cohomology of X times X prime. And here you have X times X prime, but you need to put a function on this product. And this is called the Thom-Sebastiani sum of F and F prime. So it has a complicated name, but it's the only sensible thing to do, which is that, okay, so you have a function on X, you have a function on X prime, and you have the sum on A1. So F Thom-Sebastiani F prime in coordinates is X prime, so this is mapped to f of x plus f of x prime. Okay. And then there's with this function of the product, there's a Q-net formula, and the comparison isomorphism is compatible with this period formula. Questions?
Are these rapid decays and also somehow morphs in some category of sheaves?
Yes, you can write this cohomology as a sheaf cohomology, and doing the an oriented real blow up, and you can also understand it in terms of perverse sheaves on A1. So I'm going to explain this in a moment. So in that respect, it really behaves like a usual singular cohomology. Okay, so yeah, so maybe now definition. What is an exponential period? So they are the coefficients of the comparison isomorphism when you work over a field which is inside the algebraic numbers. Okay. What does it mean? It means a complex number is an exponential period if you can find a variety, subvariety, and a function, everything defined over Q bar, in such a way that there's a class in the rank homology, there's a cycle and rapid decay homology, and when you pair them, you get the number you started with. Okay. So let's do a few examples. Yeah, so kind of zero examples. I told you that for f equals to 0, or for f constant, actually, let's take f constant. The rank homology is usual, the rank homology. Rapid decay cohomology is also usual singular cohomology, because if f is constant, then real part of f bigger than t will be 0, or it will be empty for t large enough. But the comparison isomorphism is not the usual comparison isomorphism, because we are considering these integrals. Okay, if f is 0, you get this integral, but if f is constant, not 0, you are multiplying by this number, right? So for this reason, exponential of alpha, or alpha algebraic, is an exponential period. Okay, it's an exponential period. It's h0 of the point with the variety minus alpha, with the function minus alpha. Okay, so the exponentials of algebraic numbers, they play a little bit the same role as algebraic numbers in the usual theory of periods. Okay, example we've already seen, the square root of pi. This is integral from minus infinity to infinity of exponential minus x squared dx. So this is a period of h1 a1 x squared. And let me give you two more examples. So one is the Bessel function. Defined as let's put the 2 pi here. Okay, so this is the integral on unit circle of exponential minus z over 2 x plus 1 over x dx over x. Okay, and then this will be an exponential period of h1 gm. Okay, you need gm for this differential form. And then the function is z over 2 x plus 1 over x. Okay, so what do I mean by this? Because there's a variable now, this is a function. So for the moment, you can just imagine that you give an algebraic value to z, okay? And then this is a period, exponential period in this sense. But which is going to be very important is that you can vary z. And if you vary z, then this will become a solution of a differential equation. So this already suggests that to one of these homologies, to an exponential motif, you should be able to attach a differential equation. Okay. We're going to see this in a moment. So this was 2. And then example 3 is Euler's constant gamma. So this is usually defined as the limits of the gaps between the partial sums of the harmonic series and the logarithm. If you write it like this, there's nothing you can do. But it also has integral representations. And one integral representation, if you work things a little bit, is, so it's a double integral of exponential minus xy dx dy. And where is this double integral? So it's the following thing. So first you do the unit square on A2. So this is y equals to 0, y equals to 1, x equals to 0, x equals to 1. So you have this square. Okay, so this is a usual relative homology cycle. You don't need a function for this. And this is the reason why we put the subvariety. So in this case, the subvariety y, in this case, x will be A2. And the subvariety y will be the union of these 4 lines. Okay, and what is more interesting is, so if you do, the function here is going to be x times y. So if you do the place where real part of x times y is equal to t, then you find something like this. So you can take this cycle, but then you can let go t go to infinity. And when you let t go to infinity, you can actually integrate on this whole quadrant. Okay, so this is actually the integral on the small square minus the integral on the bigger quadrant. This is Euler's gamma, and it's also an exponential period. So in this case, it's h2 of a2 relative to these 4 lines, and the function is x times y. Questions?
Actually, sorry, is this the Euler-Mascheroni constant?
Yes. I used to call it like this, but then I did a bit of research, and it seems that Mascheroni didn't do anything at all with this constant, so I'm removing him from the story. Okay, so exponential motifs. Okay, well, let's write down the theorem. So this is work with lesson. And the theorem is that there exists a category it's always I'm always a bit uncomfortable stating the theorems like this because I mean, what it means is that we constructed, right? It's not so an abstract statement. So this is a Q-linear neutral Danakian category. X K. Remember, K is always a subfield of the complex numbers. We are going to call the category of exponential motifs over K. Okay, so it has a number of properties. So one of the most important ones I already told you, which is this is a Danakian category, so it's equivalent to the representations of some affine group scheme over Q. But let me give you more properties. Okay, so the first one is that mx contains h and x y f or x y f as before, and actually every object is a sub-object of those. So somehow these are the elementary blocks of the category. Too late. Secondly, the category comes with some factors to vector spaces over K and to vector spaces over Q. This is called the RAM realization factor and the rapid decay realization factor. As you can imagine, the object H and X, Y, F is going to be mapped to the RAM cohomology here and to rapid decay homology here. And comparison isomorphism leads to a complex point. So we can look at the tensor isomorphisms between the RAM. So the RAM takes place in vector spaces over Q. So you can do rapid decay tensor K. So this is a scheme over K. And this scheme contains a complex point, which is a isomorphism between the RAM tensor C and rapid decay tensor C. And this isomorphism is precisely the comparison isomorphism I explained before. And point number 3. This category is not completely exotic. It contains the category of Norrie motifs. Norrie's category MK as a full category. Okay, and then I will usually refer to objects in this category as classical motifs. Any questions about the statement?
Well, maybe one. I'm not familiar with these formats, so it might be stupid, but when you say that that's a scheme, the isomorphisms between those two functors, and you have a C point, so I imagine that means the point is defined over some finally generated extension of Q. And so does it mean that every such, every isomorphism between the RAM and rapid decay cohomology is defined over that field? Impossible to say what that will be.
Yeah, so this is not at all stupid, all the contrary. It depends. It really depends what you are doing. So here, the way I was writing it, I'm looking at these functors on the whole category. Okay, and then well, it's quite mysterious. So typically K is inside. Let's say K is equal to Q. Okay. So this is a scheme over Q. We know that it has a complex point. So we know it has a Q bar point. We also know it does not have a Q point, but there's a Q bar point, but no idea what this Q bar point is. So we don't know how to write it down. Actually, it's very hard to write down anything here. It's you should think of this as generalizing Galois theory, and if you consider the Galois group of Q bar over Q, okay, we know the identity, we know complex conjugation, and we know that there are many quotients. So this is a huge group, but it's very hard to write down an element. So here the situation is a little bit the same if you work with the whole thing. So what we usually do, and this is exactly what I wanted to say next, is you take a motive. Instead of working on this huge category, you take a kind of like aim. Okay, so for example, H and X comma F. And then you consider all things that can be obtained from M by doing tensor products and sub-objects, sub-quotients, direct sums, and so on. So this is the Tanakian category generated by M. And this one is isomorphic to the representation of a group. And this group is an algebraic group, is just inside GL rapid decay applied to M. Okay, so in this case, you look at rapid decay cohomology, you look at the GL of this vector space, and it will be a subgroup inside. And in this case, this point is defined exactly over the field generated by the periods of M. Like the coordinates of this point are the periods. So field of definition is the field of periods of, so Q bar of periods of M. Okay. And then the situation is the following. So this group is actually defined as the automorphism of this functor. So if you have something like this, you can compose with an automorphism. So this gives a torsor. So this space has the same dimension of this group. Okay. So the dimension of the space is the dimension of the group. And then, well, you know that if you have some scheme, you have a point. If it is a generic point, then the transfluence degree of the residue field is the dimension of the scheme. So the true conjecture, if I may, is that this point is a generic point. And then you find that this should be equal to the dimension. And this is the conjecture I wanted to do. So this is the motivation from the beginning, is to take this conjecture, and now with this formalism you can formulate it. Okay. Any other questions?
Construction of this category also similar, like for Norway modules, we use some fundamental or basic level of all this.
Yeah, it's very similar. And since you already got a course by Swan, I'm not going to insist very much on this. So you use a quiver, which is the same, but you put the function f. There's the formal part, and you get an abelian category, and then you need to prove a basic lemma to prove that there's a tensor product. So yeah, so part of it is to prove that every object is a sub-object of those. This is not general, and to prove that it's a full subcategory, this is not formal either. But the rest is quite simple. Okay, so instead of telling you what is not surprising, I'm going to tell you what is surprising. Surprising means it surprised me. Surprising? Okay, so number one is this object. So recall the period of this was the square root of pi. And okay, a square root of pi to the square is pi. So, and pi is a period. So you should expect that something funny is going to happen if you take this tensor square. Okay, so remember the Q-net formula. So this says that this is H2 of A2 with the function x squared plus y squared. Okay, so this corresponds if you do the square. So you find that this is the integral on, you use Fubini, and you find this integral. Okay, and what does it mean, r squared? Okay, r squared means that you have the function x squared plus y squared. This is the region where x squared plus y squared is equal to t. So you can take the circle. It has a boundary where x squared plus y squared is equal to t, and then you let the t go to infinity, and these circles give you R2. Okay, so this is actually a class in rapid decay homology. Okay, so you see that this looks like an exponential motive. There is a function, and there's a function which is non-zero, but you compute the integral and this pi, and there's no exponential inside pi. So how do you compute this? You do a change of variables, so you change to polar coordinates and you find pi. And you can do exactly the same with the motif, and then you find that this is the x1 of x squared plus y squared equals to 1. Okay, this is a variety, and then no function. Zero function. Okay. So this is surprising for two reasons. The first reason is it means that a motive with a non-zero function can be classical, can be isomorphic to a classical motif. Number one. And number two is that this has dimension 1. And there's a bit of arithmetic subtlety, but if you think that K is Q of I, for example, then you can write this as UB is equal to 1, doing the change of variable x plus y, x plus iy times x minus iy. And this is just GM. So this as a Hodge structure, for example, is Q of minus 1. And as a Galois representation, this is the cyclotomic character. And none of these things has a square root. Okay? And most obvious is this one. So this will be a Hodge structure of type 1/2, 1/2. This does not exist. And similar cyclotomic character have no square root. So it means that there is no realization Hodge Galois realization. At least if you want these to take values in the usual categories, and if you want them to be compatible with tensor product, because then you cannot send this object to anything. Okay, so this is a bit surprising. Second surprise is that so I told you that MK is a full subcategory of MXK, but the image is not stable under extensions. Not stable under extension. Inside MX. Okay. In other words, you can have two classical motifs and an extension between them, which is not a classical motif. And the example is actually given by the gamma Euler's gamma constant. So Euler's gamma constant is a period of an exponential motif of dimension 2. And this motif is an extension of Q minus 1, which is classical, by Q0. Okay, so actually, you can choose bases in such a way that the period matrix is 1, gamma, 0, and 2 pi I. And you can prove that this is not a classical motif, which fits with the fact that in the world of classical motifs, the extensions here are rather given by logarithms. And maybe especially for Jacob, this is even a everywhere unramified extension. So it's an exponential mixtape motif over 7. That was also pretty surprising. Questions?
Do you have any hope of extending, maybe enlarging the categories of our structure of our representation to define the representation concept?
I have a lot of hopes, that's for sure. There is a bit of shadows of Hodge theory. This is something called irregular Hodge theory. And so it doesn't work as well as the usual case, but at least you can define things like Hodge numbers. A filtration. Yeah, so this thing is much more mysterious, and I don't really know what's the thing to do. And in particular, the most disturbing thing is that I don't know how to define an L function of an exponential motif over Q. So this I will really. Okay, so well, this opens many directions. I only have 10 minutes left, so I just will tell you something which kind of solves this question. Okay, so here we have a motif with non-zero function, but it's isomorphic to a classical motif. So we would like to understand when this happens. And this is something given by the perverse realization. Okay, so I told you you can associate a differential equation to an exponential model. This is kind of the Betty side of the story in terms of perversives. So the category in question is called perv zero. So it's a subcategory of, so this will be a subcategory of perversives on the affine line. So it's complex affine line of rational coefficients. And it's actually those with no cohomology. So you can take the direct image to the point, and you want that the direct image vanishes. But it happens that the objects of this category are a little bit easier than the general perversive, because they are just concentrated in 1 degree. Maybe let me write like this. They are concentrated in 1 degree, which is -1. And F is a constructible sheaf. And the condition is that F has no cohomology, only one. Okay. So this has a very, very concrete description. So you have a finite set of singularities. You have a local system out of them. You have fibers at the singular points. They glue to the local system, and numerically you can check if cohomology vanishes or not. Okay. And so what is an example of an object of this category? So you can take out some point on the affine line. You have the inclusion into the affine line, and then you do extension by 0 of the constant sheaf. Okay, you put it in degree -1. So this is your constructible sheaf, and what I'm saying is that it has no cohomology. So this is sometimes this is denoted ES by us, and it's an object L. And then I guess the statement is that there's a realization factor that goes from exponential motifs to this category, and that factors rapid decay cohomology. Okay, so here you have a factor to vector spaces over Q, and the composition of these two will be a rapid decay cohomology. And okay, so let me try to tell you where it sends an object Hn x is this to F. All right, so you do the following thing. Let's do it. So, okay, recall x goes to A1. So here you have the constant sheaf, and you start by taking the image of the constant sheaf. So it's a complex of constructible sheaves on A1. Well, you want a perverse sheaf, we know how to do this. You take a cohomology with respect to the perverse T structure. Okay. So this is a perverse sheaf, but I'm using the same n as here, but in general it has cohomology. So then you need to do an extra operation that kills the cohomology, and this extra operation is additive convolution with E0. Okay, so E0 is so there's a hole at 0, and everywhere else is the stock is Q, and this is additive convolution. Okay, which is defined using that A1 is a group. So what you do is you take two shifts on A1, you do the external product on A2, and then you use the sum math to go back to A1. Okay, so this is a object of curve zero. And let's see what happens if f is equal to 0. So if f is equal to 0, so this is the constant function 0. So it means you will find the cohomology of x, but as a skyscraper shift at 0. It's a typical example of something with cohomology, a skyscraper shift. And then, well, the skyscraper shift at 0 is the unit object for additive convolution. So when you do this operation, what you find is a sum of copies of V0. Okay. Actually, this is a Tanakian category with respect to additive convolution, and this is the unit object of the Tanakian category. So what you find is a trivial representation. Okay, this is you just see this from the formula, and I will end with the theorem. So the theorem that we prove is that this is if and only if. So an object of mx comes from mk. So it's isomorphic to a classical motif if and only if this perverse realization is trivial. And this is what I like in this statement is that it's a very simple question to very simple answer to the general question, and it also happens to be very useful in application. So I use this to prove at least two results that have nothing to do with exponential motifs. So this was in both cases the key point to prove those results. Okay, that's it. Thank you. And questions, of course, if you have.
Said, let's say for normal models, there are subcategories where chain conjecture and Hodge conjecture are better known than otherwise. So, what are the nice guys in NLOX?
Yeah. So, so as I said, the category is constructed using Norris formalism. Very good for Tanakian aspects. We get a Tanakian category. It is also very good to construct realization factors because comes very easily from the universal property of knowing motifs. And what is very bad for is to get any kind of control on morphisms. If you want to get a control on morphisms, then the reasonable thing to do is to do something in the style of Voevodsky motifs. And this gives you some idea of what you have to do. So the idea is to replace perversities by Voevodsky motifs over A1, and then consider those with no direct image to the point to usual motifs is 0. Okay, so this this has been done so first by Martin Gallagher and Simon Pepin, and then by Jacob and Timo Richards. And in that category, at least you can compute the morphisms. So for example, you find that this is the only new extension. And yeah, so then I guess you can try to ask these questions of like vanishing or but it's not very clear. From the point of view of purity, for example, a situation where things are easier is when the map F is proper. So X smooth F proper is somehow the analog of a pure motif. So those are definitely easier to study. Yeah, then yeah, I wouldn't know.
So,
Yeah.
another question. So, do we know exponential or Cho group?
So we know how to define it. You can do some little examples to get an idea of what it could be, and it seems to be like non-trivial mix of classical Chow groups. Typically, you will find so x equals to a1, and here you have f equals to 0. And typically, at least in the examples I had a look at, you find some extensions of Chow groups, or more generally K theory of x and of f equals to 0. I think it's very interesting. Do you do this in your paper? Not really, no. Yeah, I think this has not been done, and it's a very interesting question to compute some of these morphisms in this category.
Questions?